I wanted to throw this slide up, so there's a couple of interesting things happening in the department, computer science department that is, over the course of the next 2 days. So tomorrow, there's our CS colloquium at 11 a.m. Debbie Theobald, she's the CEO of a robotics company out in the Boston area, and is the recipient of this year's Computing That Serves Award, mostly because of her work on a nonprofit that she also runs. And she's been doing some very interesting things in health informatics. So I would encourage you to, if you like, come check that out. I think for those of us that are interested in trying to use technology to make the world a better place, Deborah is a particularly inspiring figure, and I think has a lot to say. It's relevant. So check that out. There's also some folks from Amazon coming, and they're giving a couple of presentations. One tomorrow night and then one Friday at noon. So feel free to check it out. Okay, let's go. We'll get started. Let's have a prayer and we'll dive right in. Can I have a volunteer? Thanks.
Our Heavenly Father, we're grateful for this day. We're grateful for the opportunity to be in this class and for the things that we've learned thus far in this semester. We're grateful for Dr. Wingate and all the effort that he puts into instructing us and teaching us the right ways to do machine learning and to implement these things to our skill set. Please bless us all be able to understand the things that he teaches today, that we'll be able to go and put them into practice. We say these things in Jesus Christ's name.
Amen. Thank you very much. So, quick note on business. I noticed, actually, I just noticed, sorry, it was pointed out to me by one of your colleagues, one of your fellow students, that the readings were a little bit messed up for this week. So I have modified them. I do want you, and I'm so sorry, I don't know what happened here. I want you to read, I think because I was switching things around, sometimes the readings didn't get switched around properly, but I want you to read a few of the original RL papers, deep RL papers. And so I will post that as soon as we have class here. In fact, I'm just going to put it in right here. I'll put it in Friday's slot here. But I want you to read the DQN paper. It's called something like Human Level Performance in Control through Jeep RL. Oh, Human Level Control. Thank you. Okay, something like that. I'll try to find the specific reference and get it to you. So please read that for this week's readings. Other than that, though, there shouldn't be anything else. Go ahead.
Are we ever going to read the paper that was previously listed?
The 1704, this archive one?
The one that was about keys.
TC, yeah, so that will go when we actually start talking about visualizing DNMs and things.
Yeah,
That's supposed to go with that.
It did seem a little off topic. That makes sense.
Because what?
I said it did seem a little off topic.
Yeah, it was totally off topic. Yeah, no, it's
Okay.
it wasn't supposed to be there. That was
All right.
not a cut and paste error. That was a wiggle around error.
Okay, yeah.
Okay, cool. Then let's continue our discussion of deep reinforcement learning. By the way, we've been working on the lab. We're still working on the specs, mostly because there's been another change. Instead of having you implement DQN, I think this is going to be too hard. We're going to have you implement an algorithm called PPO, which is a proximal policy optimization algorithm. And I think it'll be much easier. So, but we're still working, we're still refining that. We're coding, my students are coding it up as we speak. Okay, so let's review a little bit about what we learned. We've been talking about reinforcement learning, which is not unsupervised and it's not supervised, it's somewhere in between. And we've introduced several concepts. So who can give me an example of an agent? Some agent.
A robot.
Robot. Give me another example.
A car.
A car. A video game avatar.
Me.
You, okay.
A drone.
A drone. Okay. How about a stock trading agent? Could be an agent, right? Okay, so there's, you can think abstractly. It doesn't have to be something physical. Okay? Agents have actions. So give me some examples of actions that these agents take.
forward.
They move forward. They trade stocks. Torques? Torques of like motors.
Bend joints.
Sorry?
Bend joints.
They bend joints, they move, okay.
Press A.
Press A, okay. Like on your old school Nintendo controller. Actually, I guess new controllers also have it, but. Okay, good. Give me an example of a reward.
Press forward.
Winning.
Not arriving destination.
Not batting, is that what you said?
Not dying.
Not dying. That is a great reward.
Put the dot where the other dot is.
Put the dot where the other dot is. Okay.
Not crashing.
Not crashing.
A gold star.
A gold star.
Making money.
Dollars. Good.
Maximize payout.
Maximize payout. Yeah, okay, good.
Dopamine.
Dopamine. Yes. Good. You guys, good, you got it. So that's fantastic. So, okay.
So,
Yeah.
rewards are also negative, right?
Rewards can be negative.
Rewards are positive or.
Yes. So pain and suffering is an example. Dying as also a reward. Yes. Okay, some sort of feedback signal from the environment. Yes. Okay, good. All right. And then finally, let's talk about value. So the value of the state is defined as the expected discounted reward for being in that state. Why do we discount? What effect does that have?
It decreases the weight of the rewards as you get further out.
Okay, right, we discount things in the future more than things that are close. Right, so that now all sums are bounded, assuming the individual immediate rewards are bounded. Good? Good. Okay, so, and then finally, we've talked about optimal, value functions, optimal policies, and optimal Q functions. So what is a policy?
Behaviors.
It's a mapping between states and actions. Okay. So function, you can have stochastic policies and deterministic policies. Okay, and we began talking about this equation right here, the Bellman equation, which says that for a given policy, the Q value being a state and an action is the expectation over successor states and actions, the immediate reward plus the discounted Q value of whatever of that successor state. Okay, that's just a mathematical definition, and that just falls out of the definition of what a Q value is, which is the expected discounted sum of future rewards. Yes?
So it might not be done this way in real life, but if you were going to code this, would it be like a recursive thing then? Like this would be
Yes.
like just calling itself.
Well, so, right, so this is a function, and this is a function, so the definition of the function relies on itself. And yes, so you can't code this up. Like this is, you can't use, this is a recursive definition, but the beauty of this is that we can use it as part of a learning signal. So we'll see. So, but let's suppose that we didn't know about the Bellman equation. How could you estimate the Q value for a particular state in action? What could you do? And let's suppose you can just teleport to states magically.
Try them all.
Try them all. Okay, what do you mean by that?
Like if your action gives you reward, then you keep like acting. I guess it's like linear approach, or depending what your action is, just try.
Okay, I think you're on the right track. I think that's quite right. Keep going. Let's do some more.
You take like the average reward that you get for every action, and then your expected value for this state action pair would be the average. Wait, sorry.
Keep going.
The average times the future states that you have, plus. Wait, sorry, I lost myself.
You're so close. You're so close. Go ahead.
Like a graph search through states, where you're like expanding on, like, searching through all possible ones, and then you give them this expected value.
Okay.
All possible states.
Yes. So that's feeling better. So remember that little, I don't know if you remember this, maybe you weren't paying attention, but in the AlphaGo trailer, there was this moment when they showed a board state. And and it like split into all these other board states, which then split into all these other board states. It's called a game tree. And I think what you're saying is you're saying, hey, if we want to know the value of a state, say this particular configuration, somehow we can look at all the successor states, and then all the successor states of those states, and then all the successor states of those states, and calculate the value. Is that what you said?
That's what I'm getting at.
That's what you're getting at. Okay, good. Good. This is the right idea.
So I was, to add to that, maybe setting a bound, so using a branch and bound method where we bound a certain reward, and so we don't have to check every state, so we don't have to be exhaustive.
If you could bound somehow, that would be cool. Yeah, so, okay, so the Monte Carlo estimate of the Q value of a state is as follows. We're at some state in our world, could be a ghost state, could be a robot state. We want to know what its value is. So we do what's called a rollout, where we start in this state, we have a policy pi, and so we know, we just look up what we're supposed to do in this state, and we take that action, and that takes us to some new state. And then we look up the action in that state, and it takes us to some new state, possibly stochastically. And we keep doing that a bunch of times, and eventually we either die or stop. Then we can teleport back here and do it again. And we'd get a different sequence of states. Why would we get a different sequence of states? Stochastic, what's stochastic? Policy is potentially stochastic. And the transitions could also potentially be stochastic. So you can do this a lot of times, and you get different sequences of states, actions, and rewards. And then you could just calculate the average of all those rewards, and that would be the expected sum of discounted future rewards. Okay, so that's called the Monte Carlo approximation to the Q value of the state. And so why is that good? Like, why is that a good way to calculate the Q value of a state? It's accurate. What do you mean by accurate?
Well, I mean, you know, I guess you've got to, the flip side is, right, obviously it's expensive.
It's expensive.
Having to do all of these simulations.
All these rollouts, yeah.
But it makes it very accurate because, right, the longer you simulate, the more simulations you do, the more it's going to represent the actual.
Right, right. There's no approximation here except in the sense of like limited data. And so this is, in terms of the language of statistics, we would say this is an unbiased estimator. So the expected value of this estimator is the true value of the state. And it's statistically consistent, meaning that in the asymptotic limit of infinite data, like it will converge to the true value, something like that. Right? So there's no approximation here. Yes, Brent?
I would actually argue that it's not expensive because you have full control over how expensive it is.
Okay.
Maybe to get some level of convergence and some confidence interval, it's expensive, but you can control that. And you don't have to go through every possible state in the sequence.
Okay, good. So let me ask you a question though, Brandon. So let's suppose you go ahead and estimate the value of the state, and you do n joules worth of work. And now I say, okay, I'd like to know the value of this state here, which is pretty similar to, but not exactly the same system. How are you going to estimate the value of the state?
So the easy way is just to repeat all that
Same thing, right?
If there's a way that you can store, and there's a relationship between those states, that you can use some of the work that you've already done.
Okay, and so I think, yes, it's true that you can tune the amount of work you're going to do for this, but I think it will always be expensive in the sense that it's very difficult to reuse work that you do for this, for any other state. You might, like maybe you could somehow find similar states in here and like somehow aggregate them and use that as, it's actually kind of hard. So, but instead what we'll see is we'll see if this is a value, you can think of it as a function, and if I tell you, here's state 1, and its value is this, maybe doing that, and then I say, here's state 2, sorry, here's state 2, and its value is this, and then I tell you, here's state 3, and its value is this, and then I tell you, here's state 4, and its value is this, and now I want to know, what's the value of state 5? What would you say? What do you wish you had if I asked you this question? This is some function. don't you wish you had a function approximator that could like somehow approximate maybe the true underlying function, and then you could just ask it what a new state was, and it would generalize to nearby states? Oh, that'd be cool, wouldn't it? Yeah, okay, so, spoiler alert. Okay, so that's called the Monte Carlo estimate of the Q-value of a state. Monte Carlo approximation, but there's also this Bellman interpretation. Or, sorry, it's not interpretation, it's just, there's additional structure here which we can take advantage of. Okay, we talked about this too. We talked about how there's such a thing as an optimal policy which achieves the maximum possible reward for any state action, for any state. And notice that if you had the optimal Q function, you could easily derive the optimal policy. We talked about that, where you just like argmax over actions. And similarly, the optimal Q function satisfies this slightly modified Bellman equation where the optimal Q value is the expectation over successor states of the immediate reward plus the discounted maximum Q value of the next state. Yes?
So if we were to do Monte Carlo, like the Monte Carlo approximation, but we did all of the possibilities, we would get, like, that would be the optimal value.
That would be the true state, yes.
Okay.
That would be the true value. So if you could brute force enumerate,
yeah.
So in theory, you could calculate this for Go. It would take like several times of several universes sort of things, but you could do it because there's a finite number of states. But for continuous state spaces, no finite amount of computation can arrive at an exact answer, unless there's some special structure to the system. Okay, so let's introduce one more concept, which is a model. So there's two big classes of reinforcement learning algorithms, model-based and model-free. It turns out one of the most fascinating things about reinforcement learning is that once you understand the structure of value functions, Q functions, and optimal Q functions, you can build agents that learn to behave optimally in systems without ever being able to predict anything about the system. Okay, so I'm just like this, I don't know, nematode or something. I'm a super dumb organism, and I'm just interacting, and I start building up these Q functions in my brain. I can learn the Q functions, and for any state, I can look up what I'm supposed to do, and I can do it, and it will be the optimal thing to do, but I can never predict what the outcome of my action will be. Okay? Kind of interesting. It's called model-free learning. The agent cannot predict the future, but it knows how to act. And when people discovered this, they were like, like their brains exploded. I thought that was really neat. And it spawned this whole series of, this whole branch of work, which was very influential for a long time because people thought this is really cool. Okay, so the thing that lets you predict the future is called a model. And it's a very simple idea. It's just if you give me a state and an action, I tell you what the next state is going to be. So in the game of Go, let's think, do we have a model for the game of Go? Who says yes? Okay, a couple of you. Who says no? Oh, it's like split. Okay, who wants to argue the no side?
Say the question again.
So in the game of Go, do we have a model? Hold on.
I was just going to say, how does the game Go work?
How does the game of Go work?
Yeah, because that might.
Oh, okay, so it's that board, the 19 by 19 grid, and you put down stones, and depending on configuration of the stones, you capture enemy stones, things like that. Okay.
I would say yes, just
Yes.
because the outcome of an event is literally the state of the board.
Okay, so you're saying because the state of the system is the state of the board,
If you
if
place
I-
a piece somewhere, you know where you placed it, so you automatically know what the state of the board is.
okay?
I think if I agree with him conditionally, I think it depends on what we define the state to be. Because if the state really is just like white piece here, black piece here, across the board, and if an action is just placing a piece, then sure, when we place a piece, we know where all the pieces are. But if our state, like we said last time, includes something about like the psychological state of the opponent and how they're going to respond to our action, then maybe there's an unknown factor there that, so, you know, their next move, we don't know that, and that could be sort of involved in their psychological state.
Good. Okay?
Well, we have a model because we know the rules and we can represent a game in the computer and we can look through all of our possible legal actions. I don't think we have a model for optimal play. Like
Right.
we don't have like we have a model, like with ODEs and stuff, you can't solve them, but it's a model.
Yeah, so you're right, we haven't, so a model is just something that lets us predict the future. A model does not tell us what to do. So I think you're right, I think you guys have got the idea. So we know the rules of the game, but we don't maybe know about our opponent. And so if I'm just thinking about the state of the board as being, sorry, if I'm just thinking about this from the perspective of, say, the white player, and I want to know, I put down my piece, what is the next board configuration going to be? I cannot predict that without knowing something about my opponent. But if we, so in that sense, I don't have a model unless I have a model of my opponent. All right, and then by the way, so then if you have a model of the system, you can do what we talked about, various rollout kinds of things, because you can mentally teleport to a state, and you can ask what would happen if I did X, Y, or Z. So you can simulate experience if you have a really good model. Yes?
So the state transitions go from, like, with Go, what you were just talking about, go from like the white player's turn to the white player's turn.
Could be, yeah.
Or you could
That's
have-
how I would define it, because I want to know what I should be doing as a player. So,
Right. But if it was from like white to then the black, to immediately after that, then those transitions would be like stochastic. But either way, we wouldn't have a model.
right. I think that's right. Unless you're something, yeah, that's right. Okay, good. So, how do we actually learn these value functions and these Q functions? How do we learn to behave while we're learning about the environment? There's three big classes of approaches. There's what's called value-based RL, policy-based RL, and model-based RL. Value-based RL is where we try to learn these value functions or Q functions, and then use those to derive a policy. Policy-based RL is where we somehow search for the optimal policy directly in the space of policies. Maybe we don't ever construct a value function or an estimate thereof. And model-based RL is where we somehow spend a bunch of time building a model of the environment. So we learn a function that maps states and actions to states. And then we use that in conjunction with some sort of planner, say some rollout-based planner, and use that to somehow construct a policy. And the idea of deep reinforcement learning is that everywhere where we say the word function, and we say, well, that we can't actually represent that function, and we need to approximate that function, we stick a deep neural net. That becomes deep reinforcement learning. So the things that you can approximate are the value function, the policy, and the model. We can use deep neural nets at all of these points to help us along the way. And so what you're gonna code up for your next lab is an example of policy-based RL. And we'll be talking about that a little bit more on Friday. Okay, so let's talk about value-based RL. This is like the most, some of the most influential RL work that I want to go through. So the idea is there's some true Q function, optimal Q function, Q star of S and A. And we're going to approximate that with some deep neural net. So you're going to give me a state and an action, and I'm going to tell you what the Q value is for that state and action. Now remember, if I have this, I know how to act optimally, because in any state, I can just ask, what's the argmax over actions of this approximate Q function? And so we've got some weights. There's actually two ways you can do this. That's what this little figure is showing. You can actually say, for a particular state action pair, what's the Q value? You can also say, for a particular state, what's the Q value of all of the actions available in that state? You can kind of set it up either way. It doesn't matter too much. You can imagine some pros and cons to these, both of these ways. So we're not going to talk about it anymore. Okay, so here's how we do Q learning and then deep Q learning. So remember, the optimal value function, sorry, the optimal Q function is supposed to obey this Bellman equation. And so the idea is very simple. If we know that for a particular state action, this is supposed to be equal to this, then we're just going to treat the right-hand side here as a target. And so what we're going to do is we're going to say, well, the Q value for a particular state action with some weights, that is supposed to be equal in expectation to reward plus gamma plus max over successor actions of the the Q value of S prime A prime. Okay, so we're trying to say, here's our function we're trying to learn. It's supposed to be equal to this. We're taking mean squared error, and then what are we going to do? How are we going to, what do we do then? So this is our loss function. Yeah, we're just like, take the gradient of this with respect to the weights. Okay, now this is a little bit funny though. Why is this a little bit different than any other loss function we've ever seen? What is unique about this loss function?
It's dependent on its own prediction.
Yeah, okay, right? This is a little bit weird. So what we're saying is the thing we're trying to learn is dependent on the thing we're trying to learn. So the target, we're also approximating the target. And so we're using the same function approximator for the target value as well as sort of like the thing we're trying to learn a little bit more about. So that's a little bit funny. Turns out it works fine. There's some, if you just do this, like it actually kind of works. But if you understand this a little bit more deeply, you can do a little bit better. Yeah.
So for this, is it kind of like so the function we're trying to approximate is based upon the function we're trying to approximate, right? Except for the actual reward value are right there.
Right. So great observation. So here's let me rephrase what you just said in terms of a question. So if the thing we're trying to approximate depends on the thing we're trying to approximate, why doesn't it just degenerate? And why doesn't everything go to 0? Because if everything was 0, then the Q value of a state would meet the Q value of the state, and that would all be 0, and then it would get 0 loss, and we'd be good, right? Why doesn't that happen?
Occasionally you'll stumble across a non-zero reward.
Right, okay. R is the only thing that saves us. So sure, this could be 0, and sure, this could be 0, but then if R is non-zero, there would be some loss. And so by tweaking our Q value to be a little bit closer to the discounted reward, we'll get better loss. And so that's the thing that keeps us, it is exactly the observation that the rewards are what's critical here. That's the only thing that keeps us learning.
So in this loss, because we have the weights in there twice, is it actually getting error from both the next action and current action?
Yeah. Yeah, absolutely.
So for like Go, the R would only occur at the very last.
Right. So in Go, how often do you get non-zero rewards? Like basically never. It's terrible. This is called reward sparsity, and it's a huge problem in learning.
So from what I remember, I was doing something with DQ learning for research, and they had the weights of that frozen.
Yes, absolutely. So this is what I was saying, right? You can actually do a little bit better if you're a little bit clever. So actually, what people actually do is they have two sets of weights. They have the target network and they have the network you're learning. And they freeze these weights. So now everything's decoupled. And you just try to learn a new Q function. And then you freeze these weights and call that your new target network, and then you keep going. And that actually works much better. Okay. Yes.
Sorry, what is the gamma here? How would that work if you were actually coding it up? Like, is that a hyperparameter, or
Yep.
is it okay?
Gamma's a hyperparameter. It's just a scalar. It's a number you pick. 0.99, something like that. Okay. Interestingly enough, so this is basic Q learning. It converges if you have a finite number of states and actions, and you can represent everything exactly. But it's actually known that this diverges in neural nets. The reason is if you don't set things up very, very carefully, because we experience sequences of states and actions over time, there's a lot of correlations between the states and the actions. And the fact that this thing, as we were just saying, if the target weights are shared with a Q function and they're not frozen, then there's non-stationarity here, and you get these weird oscillating things that can happen. But there's practical tips and tricks to sort of get around both of those things. Yeah?
So
does that have enough states and actions to potentially get to a reward? Like, does it have to enroll enough so that you can get to a reward before taking your next iteration?
Okay, yeah, so
Just
notice.
a move at a time, there will be a lot where it's non-zero,
Yep,
non-zero.
yep. So, yeah, so good question. So notice there's no rollouts here. At every time step, we see a state, we see an action, and we can ask what the max over the next state action pair is. So we can potentially do stochastic gradient descent online as we're interacting with the world. In practice, that doesn't work at all. But there's no rollouts at all. So yes, we could, in theory, update this at every time step. But you're right, if we are in a domain where there's sparse rewards, a lot of this it'll be kind of funny. We'll see a lot of zeros, everything will want to go to zero, and then we'll see a non-zero and everything will spike up. Okay, so practically, there's other things that we do to get around that. Specifically, this thing called experience replay. So the fact that we have, the fact that there's all these strong correlations and reward sparsity in our experience stream means that we need to cope with that. So the way that people do this is they basically just build a big data set. It's called your experience. And then you pull things out of your experience. So you start with a stream of state action reward, and you split it into experience quadruplets. So this is the first state action reward state, second state action reward state, and you just put this all into a big database of like 1 million data points. And then what you do is you go ahead and do gradient descent, stochastic gradient descent on this, but sampling from your experience uniformly. So you sample a mini batch from what you've experienced so far, and then do stochastic gradient descent, and then do the weight freezing thing. So this is great because it breaks the temporal correlations here, because now we're sampling from experience from all of the different times, so the states and actions are uncorrelated, and we get rid of the moving target thing by freezing the weights. So those are two big insights to make DeepRL actually work. Yes?
So when we take things from our experience replay and put them into the equation, which things from I guess, ST, AT, et cetera, where do they go into that equation?
Yeah, okay, can you guess?
I would guess that ST and AT go to S prime and A prime.
Okay, well, ST, AT, RT plus 1, ST plus 1. So I was in this state, I took this action, I got this reward, and I ended up in this state. That's how you read that. So yeah, so how do these map to this equation? Good question. Your answer was wrong, but do you want to try again?
Sure. I'm pretty sure the reward goes in our reward.
Okay, R and R, good.
And I guess our S and A, our ST and AT, do they go to Q of S and A?
Yes. So I was in this state and I took this action. I transitioned to this state, which is S prime. And where does A prime come from? Yeah, we're maxing over A prime here.
Gotcha.
Okay, so we're going to ask our network for however many actions we have. We're going to ask it what the Q value is, and we're going to take the max. And then that just becomes a number. And so then this number is supposed to equal this stuff. Yeah?
So, if I understand the freezing part right, so we were like, for coding stuff, we would grab this big random batch of experience replay, like 100 samples we have, and then we calculate the loss for each of those state action or quadruplets.
Mm-hmm.
But we have like an existing best model. Is that what that means? The frozen thing. And then we have like our model we're trying to continue to train.
Mm-hmm.
And then the next time step, the existing best model is the one we just barely updated for the last time step.
It's more like you guess at some weights, and then you use that as your target network. Or actually, the best thing you should do is train your initial Q network on just the immediate rewards. So for a particular state in action, just pretend that the sum of discounted future rewards is just the first reward. So then there's just a supervised learning problem. But then what you do, so you train for freeze one network, but then you train for a while. So sample a bunch of bunch of mini batches, you train your new weights over time, and then you discard those old weights, freeze the weights you just learned, and then start some new weights. But you train it for more than one mini batch. You train for a while.
So you might be getting to this, but assuming you're doing this like online, while playing, say Go, so maybe what you're going to be doing is you're going to go through a few games, doing random actions, and getting your rewards, and you're going to save all that, and then just sample from what you saved,
Yep.
and train on that.
Yep, you got it. So notice the statistics of this experience database depend heavily on what's called your behavior policy. So for example, if my policy is just that is going to introduce bias here. So yeah, so this depends on your behavior policy. Okay, good. So here's, I'm going to take you through now the DQN paper. Go ahead.
If we have a model, we don't need experience, right?
Right. If you have a really good model, then in theory what you can do is you can mentally ask for any state, what would have happened? I can take a state and an action and get the reward in the next state. Like that's what a model does. And so I can get rid of the experience database and I can just sample a bunch of states, ask what the consequences of doing certain actions in those states is, and then put that into my loss function and away we go. Yep. So that's right. So in one sense, this experience database is like an approximate model of the world. It's just a data version. Okay, so let's talk about making video game playing agents. So let's suppose you want to play an Atari video game. So what's the state space? State space is? Pixels. How many pixels? A lot of pixels? Be more specific. Let me ask you this. If I show you a single screenshot of a video game, say Space Invaders, is that enough to tell you, is that enough to know what the state of the system is? No. No, why not? Okay, because can you tell me if the enemies are moving left or right? No, you can't. I mean, maybe like, I don't know, their feet are all pointing left. Maybe that's a signal. Probably is actually, but pretend that they're not. Pretend that they're symmetric. Anyways, yeah. So a single screenshot is not quite enough to have state. If you want to know the direction that they're going, how many screenshots do you need? Two. If you want to know their acceleration, how many screenshots do you need? Three. Very good. Okay, so this is called. This system is not fully observed. So in other words, there's some hidden state information which you don't observe directly by looking at pixels, but it is what's called kth order Markov, where k here is like 2. Okay, so if I just remember the last 2 frames and call that my state, then I have all the information I need in order to predict the future. In practice, they remember like the last 4 frames. Okay, so that's the state. What's the reward? Score. And what's the action space?
Left, right, shoot.
A, B, A, B, select, start. Yeah, so it's whatever the control space of the game is. Okay, and so all we have to do is take the concepts that we've learned and throw it all together, and we will have state-of-the-art video game playing agents. So the paper that sort of unlocked all of this was this paper that I want you all to read, the DQN paper in Nature, a couple of years ago now. And they are the first people to get convolutional deep neural nets working in RL for video game playing. And so the idea is we are just going to learn straight from pixels we're going to go from pixels to actions. Right? And that is the Q function. Q function accepts as inputs states, which is pixels, and it's going to output actions, which is left, right, A, B, select, start, whatever. And so this is their topology. It's actually a surprisingly simple topology. So they take a stack of 4 frames, they resize them to 84 by 84 pixels, and then a couple layers of convolutions, 2 fully connected layers, and you're done. So this is like, you guys code this in your sleep. And then the reward is just whatever the change in score is, so just delta score. That's it. And then they do the freezing the weight targets and the experience replay, and away you go. And the results were very impressive. So the reason that this is called human level performance in Atari video games is because they were able to build an agent that beat human performance on almost all of this battery of games that they tested on. So here's, I think, 40 or so games. This line right here represents human level performance. So everything to the left, the agent does better than a human. Everything to the right, the human did better than the agent. By the way, this result is maybe 4 years old now. And now, like, RL agents dominate. They totally dominate all of this. I mean, you've probably seen the news. We're much, much better than humans at all these games. Although it was interesting to me. My friends who work at DeepMind, where this work was done, they said, I said, well, how did you get the human level performance? And they said, we have a guy. Like, his job was to sit there and play Atari video games all day and calculate the baselines.